Hello, good evening. Am I audible? So, good evening and welcome to all the students in this session of quantum mechanics. Already, we had one session on introduction of quantum mechanics. Why quantum mechanics? What are the different aspects of quantum mechanics and how this quantum mechanics is useful as a physicist or as a student of physics or sciences. So that is what we have discussed in earlier lecture, and today we will be just trying to discuss some of the important aspects of the quantum mechanics in view of NET and SET examination. So once again, thank you, Barty, for giving me an opportunity to share my ideas on this particular topic, and especially thanks to Mr. Rajiv Gandhi sir for conducting this session very smoothly. So, if we see the syllabus of NET and SET, then we can see they have covered the basic to advance of the quantum mechanics. As we know, the quantum mechanics is very huge subject, but again, to understand the advance of quantum mechanics, we need to understand some basics of quantum mechanics also. And if we don't have the basic, then it is always difficult to understand the like a quantum mechanics. And if we see the quantum mechanics, then quantum mechanics is always divided into two parts, like we called as a wave mechanics, and another one is the matrix mechanics. And again, with the help of these two different theories, we can solve the different problems of the quantum mechanics. So somewhere we can use the wave mechanics or some for solving some of the problems where we are having more than three dimensions. Then we go for the matrix mechanics, and then we know to solve the matrix we need different notations and different kinds of the aspects, and that also we'll be trying to discuss in this incoming sessions. So when we talk about quantum mechanics, then what should come in our mind initially? So the always question arises why this particular physics comes into picture around 1900. Then again, what was the inadequacy of the classical mechanics, and because of these all inadequacies leads to the development of new physics, and that is what we called as a quantum mechanics. So, friends, if we talk about classical mechanics, or if the scientists try to extend the ideas or the theories or the concept of classical mechanics to numerous problems, then they found that cannot be extended, or with the help of classical mechanics we cannot solve some of the problems. And the first problem was like a black body radiation. And if we see the spectrum of black body radiation, then we can see some like a discreteness is there. And discreteness is the identity of, we can say, the quantum mechanics. So where means, because that if there were no discreteness, or the like a means there, like if the like if we see the spectrum, if it could not have the continuum, then definitely nobody thought about the quantum mechanics. And that because of this kind of the discreteness, there was a evolution of new kind of the physics, and we called as a quantum. So quantum, and as if we see the word itself, so quantum means that comes from the quanta, and as we know, if we see the wave packets, and then we called as a quanta, or the, and then again the mechanics is, as we know, the study of the motion. So when we are dealing with the light or the photon, and if we are just trying to explain the phenomenon associated with the photon, then we cannot explain very particularly with the help of classical mechanics. And that is why there was the emergence of new kind of the physics. And simply you can elaborate these terms like a quanta comes from like quantum comes from the quanta. And then, or like another meaning of quantum is sudden. So that is again literary meaning of the quantum. Suddenly it comes into the picture around 1900. So that is why these are the two aspects. Because of this, the name is like quantum. So friends, like if we see the black body radiation spectrum, then we can see some discreteness is there. And to resolve the discreteness, we need a new kind of the physics. So that also you might be knowing, and you can just went back to some theories of radiation, then you will come to know, or you can understand. understand, or I think in previous topic also we have seen. So another thing is that, so again, when as you may be knowing, the Einstein has given the phenomenon of the photoelectric effect, and for which he awarded the Nobel Prize also. Not for what, he was not awarded a Nobel Prize for E is equal to mc square or the relativity. So, friends, and again, as we know, if we see the photoelectric effect, then we know when light falls on any of the metal surface, then there is a ejection of an electron from the metal surface, and it's really difficult to explain this kind of the phenomenon with the help of classical mechanics, because if there is ejection of an electron from metal surfaces, then what will happen with the energy of the liberated electrons or the incident electron and all, so and the difference of the energies, so that cannot be calculated with the help of classical mechanics, and that is why again there was a emergence of quantum mechanics. So that was another reason. Then again, another reason we can see here, that provides the evidences of the wave nature of electrons and describe how their wavelength depends on the speed. And as we know, there is one famous equation, lambda is equal to h by p, or lambda is equal to h by mv, and we called it as a de Broglie's hypothesis or the de Broglie's wavelength. So friends, as we know, when we are talking about light, then we are always saying that light is having a dual nature. And dual nature means what? Light is having the wave nature as well as light is having the particle nature. And if we go with the wave nature of the light, then we know there are certain phenomena like interference, diffraction, polarization. So these are the simple phenomena like refraction, reflection, and these all phenomena gives the evidences or gives the confirmation of light as a wave nature. But whereas if we want to study light as a particle, then how do we explain it? Then it is always difficult. So to explain light as a particle nature, then really this particular de Broglie's hypothesis matters, like a de Broglie hypothesis matters a lot. And again, as we know, the waves associated with like a matter or like any of the particle, then we call it as a matter waves. And this is the new kind of the concept came into the picture or given by or explained by the de Broglie's. So this is again another theory or the another experiments, as we know, the Davison and Germer experiment, which leads or which gives the evidences as well. Even we are using the X-ray or when we are using the electron, then how do we calculate the potentials, or the potentials or the wavelength associated with both, and then that is just approximately same, and that gives the evidences of particle nature of light also. And again, as we know, because of this all like a quantum mechanical phenomenon, we are having so many instrumentation in the field of material science, like a scanning electron microscopy or the scanning tunneling electron microscopy or the AFM atomic force microscopy. Because without microscopy, it is very much difficult to understand the particle size. And if we don't understand, then really, as we know, how difficult to explain the behavior of that particle also. So friends, that is why this all phenomenon matters a lot. Then again, this particular kind of the physics describes the radioactive decay, fission and fusion in terms of nuclear binding energy, and again mass defect, and that can be explained with the help of Einstein's famous equation E is equal to mc square. And again, this is then again, as you may be knowing, there are two different kind of the quantum mechanics will be there, like a relativistic as well as the non-relativistic quantum mechanics. So that also we will see how these are deeper from each other. But again, at the beginning of this particular lecture or the session, I am telling you, if you develop your basics or the fundamentals very meticulously, then it is very much easier to solve the problems. But if you only focus on questions or the MCQ type of the questions, and then you will think to qualify the competitive examinations, then really it will be difficult. So build your basic, and then definitely we can have some means we can solve easily the MCQs. So now if we talk about the challenges of quantum mechanics, so then what are the different challenges of the quantum mechanics? So then we can see, if we are talking about classical mechanics, if we are just taking the example of cricket ball, or if we are taking the example of any of the vehicle, then how the trajectory, how the motion of the vehicle, that can be seen by the naked eyes, or that we can observe. But if we go for quantum mechanics or the quantum mechanical phenomena, then we know the things are very difficult to understand, because that we cannot observe. But now there are so many ways, like with the help of screen we can observe. As we know, if we want to study the electron, then it is always difficult. But if we are having some screen coated by some fluorescent or the phosphor material, then definitely we can see how the trajectory will be there. So that is why we can see how it is difficult to understand. So like you can see here, classical physics rewards students who can picture what is happening, whereas quantum theory defines visualization. So if our visualization is very good, then definitely we can have lots of understanding from the quantum mechanics, and that is why quantum mechanics differ from the classical mechanics. Again, another thing is that abstract and the counterintuitive ideas need to be linked to visible phenomena and devices, including some already familiar to students. If we are taking the example of Heisenberg's uncertainty principle, then we know we are talking in terms of delta x into delta px is greater than or equal to h by 2 pi. But if we want to prove that, then how do we prove? Then the very simple kind of the things we are taking to understand and explain this particular phenomena, and that we called as a thought experiment. And if we go with thought experiment, then definitely we can see or we can understand how this particular phenomenon is there. And if we are talking about Heisenberg's uncertainty principle, then we can say that it is very much difficult to explain or the state the either position and the momentum of a microparticle with exactness and simultaneously. Means at the same time we cannot tell about the position as well as the momentum with exactness, but at different position we can tell about the momentum, we can tell about the like a position also. But if we are thinking, if we are taking the example of classical particle, like as I told you, as I have shared, if we are taking the example of cricket ball or the football, then we can see both. We can calculate the momentum as well as we can see the position of the like a macro body, but it is not true, or it is very much difficult for the micro bodies. And that is why again some different kind of the mechanics and theories are involved in quantum mechanics. Then again, the most A-level specifications trivialize the teaching of quantum. Yeah, as we know how this particular physics is differ from the classical mechanics. Then again, if we are talking about scientific explanation which gives support for the existence of quantum mechanics, then simply we can have the correlation of the separate observations. So we can correlate two things. As we know, if we if we study in detail about the thought experiment, then we can understand the position, we can understand the momentum, and then we can correlate both the things, and then finally we can conclude that like delta x into delta px is greater than or equal to h by 2 pi. And simply we can see, because of this type of the observations, we can have some new set of equations or new set of relations, and a new kind of the directions which leads for the development of the different which leads for the development of the theories that can supports the practical, or the practical can supports the theory which was thought by the like a physicist. And that is why in that way the quantum mechanics developed from 1900 to till date. Still it is developing mechanics, we can say that it is not completely developed mechanics. Again, some people are talking, again there would be some different kind of the phenomena, and then they are saying that that theory is called as a chaos theory, or like they are saying that particular kind of the theory is as a string theory. So again, this is new kind of the physics, and we can explain, or we can see how it will just develop, and how we can accept that kind of the physics also. Because now, as we know, because of development in science and technology, we can have study of n dimensions. So earlier it was really difficult, and that is why we were thinking about the like a 3 dimensions, then 4, 5, 6 dimensions. But now people are thinking beyond that. And again, if we solve this type of the problems, then we know the matrix mechanics that is already developed in quantum mechanics can help us a lot. So this is what we can see about the like a basic or the basic idea about the quantum mechanics. Then again, as we know, if we are talking about quantum mechanics, then we are always dealing with the microparticles. So we are talking about electron, we are talking about the photon, we are talking about the neutron, or like a proton, or again a subatomic particle also, as you may be knowing about hepton, and like number of particles which are present inside the nucleus. And if we want to study their behavior, if we want to study their mechanics, then definitely, as we know, the quantum mechanics helps us a lot, and that is why we can say that the small things are weird. So how it will behave, in which direction it will be moving, or how their trajectory will be, so it's very much difficult to understand, and that is why that can be only explained with the help of quantum mechanics. And even though you may be knowing about the statistical mechanics, where we can study the motion of a gas molecule, and if we want to study the number of molecules which are present inside any of the chamber, then we know we are having different statistics like a B, FD, and MB. But when we are dealing with very much small particles, we call it as a microparticle, then we go for the FD statistics, and as we know, this is the quantum statistics. So like Fermi Dirac statistics, and that can explain like a behavior of the gas or gas molecules with the help of the quantum mechanics. So friends, again, if we see in detail about the quantum mechanics view, then simply as we know, like every matter, or we call it as a particle, has wave-like properties, and so that is why we called it a particle wave duality. So earlier we thought the if we are throwing any of the like a particle or like any of the ball, then there should not be association of any waves. But quantum mechanics proves if there is a particle, then there is a wave. If there is a wave, then there is a particle, and that is what we call as a duality. And that duality proves or like gives number of confirmatory evidences when a number of scientists tried to understand the phenomenon of the light. Then they extended various theories, and then as we know, if we want to understand the wave theory, then they have applied different phenomena, as I have just discussed earlier. So again, if we see the particle and the waves, or the particle waves are described in a probabilistic manner. Again, one more thing I am telling you, I am just trying to share with you. Quantum mechanics is almost probabilistic mechanics. So on the basis of a probability, that mechanics was developed. But again, when scientists tried to, or the research and development community tried to perform some experiment, then they got some evidences for the theories which were developed earlier, and that is why we can say that quantum mechanics is a probabilistic mechanics. And simply we can see like a electron doesn't be around the nucleus, it has a probability distribution describing where it might be found. So simply, as you may be knowing, quantum mechanics has supported to the Bohr's theory. Bohr's theory, what it says, the electron is revolving around the nucleus, but there was no evidence. So how the electron can be revolving around the nucleus? But when like quantum mechanics came into the picture, then with the help of Heisenberg's uncertainty principle, it has been proved that if we are trying to calculate the energy associated with any of the particle which is moving, like not any of the particle, but the electron moving around the nucleus, and if they tried to calculate, and they are getting some values around 4 MeV, and on the basis of that they have confirmed that electron cannot reside inside the nucleus, and that is why finally they have concluded electron must be revolving around the nucleus. So, and again, as we know, like this particle waves theory also allows the like seemingly impossible quantum tunneling. As you may be knowing, the tunnel effect that we can explain with the help of one dimensional, like a Schrodinger's time independent equation. If we explain the quantum tunneling, then we know how any of the object having the low energy in comparison to the barrier, but beyond that, that object can cross the barrier. So that is what we know the phenomenon of the quantum tunneling. And again, as we know that quantum tunneling is used in various applications, like you may be knowing about the tunnel diode or the like a STEM, scanning tunneling electron microscope. So in that way, the number of applications are there where quantum mechanics or the theories which were developed in quantum mechanics can be extended or can be applied. And in that way you can see the how quantum mechanics is important mechanics and how it is applicable to everywhere. So then again you can see some properties come in dual packages, like can't know both simultaneously to arbitrary precision. So simply we know the Heisenberg's uncertainty principle. As I told you, or as I have shared with you, like delta x means the position, uncertainty in position. That delta x is what? It's uncertainty in position into uncertainty in momentum. Delta px is greater than or equal to h by 2 pi or the h cross. And it's as we know, so the measurement of the position or the measurement of the momentum is very much difficult with at most precision. And that is why like a position, momentum, and energy or the time are the examples of the pair. So position momentum like that delta E into delta T, so again is greater than or equal to h cross. So that also comes into the pair, and that gives us more elaborative explanation and the confirmation for the Heisenberg's uncertainty principle. Then the act of measurement fundamentally alters the system. So as we know, so called as entanglement. So now you may be knowing recently the Nobel Prize was awarded for the quantum entanglement. So you can see, you can read that paper in detail. So you must be getting again more insight about the quantum mechanics. So like information exchange alters a particle state also. So these are some of the evidences, or these are some of the theories or like a quantum mechanics views that gives or that gives us the support for understanding and like for just accepting quantum mechanics as a physics. And then again now you can see some of the theories we can see here, like why don't atoms disintegrate in nanoseconds? Like if electron is orbiting, it's accelerating, and then simply we can see if electron is orbiting then it must be accelerating. Or some of the, as we know, the electromagnetic radiations you may be knowing, that just always begin from the radio waves and end up at a gamma radiations in terms of increase in frequency. Like a radio wave is having a lowest frequency, whereas gamma radiation is having a highest frequency. And now how, if we see the spectrum, if we see the behavior of this particular electromagnetic radiation, then we know the wave nature is dominant towards the radio waves, whereas particle nature is dominant towards the gamma radiations. And in that way, if we see the visible region, then we can observe both the phenomena in between in a visible region, like a wave as well as a particle nature. So these were again another fundamental aspects of the quantum mechanics. And again, if we see the like a pre-quantum problems, like why was red light incapable of knocking electrons out of certain materials, no matter how bright? So as we know, if we see the electron like Weib-Guyer, like violet to red is having, you may be knowing, 614 or around 600 nanometer, or the 6000 Armstrong is the wavelength. But again, you can see how that red light can be incapable of knocking the electrons out of certain materials. Whereas if we go towards this side, like ultraviolet, then that can. So again, it depends upon the energy, because if we see, if we take the example of Weib-Guyer, then red is having the like you can see the frequency is simply we know. So in which direction it will be more, which means that this has a less energy we can see. So at blue light could be readily do so even at modest intensities. And as we know, that can be explained with the help of the photoelectric effect, and that was just explained in terms of the photon. And as we know, the Einstein won the Nobel Prize for for the explanation of photoelectric effect. You can see simply, if we are taking the 700 nanometer light, and if we just fall this light on a target, target can be taken as a metal. So here target is taken as a potassium, then simply you can see there is no emission. But if we take the light of 550 nanometer, then you can see here there is a ejection of an electron. Again, if we go just below to that, like 400 nanometer, where we can see the blue color, then again you can see here there is a ejection of an electron. And then again we can have some like a maximum potential at which it can liberate or eject the electron and all. So this kind of the basic you have to develop if you think about quantum mechanics. Otherwise really it is very much difficult to understand why and how it is happening. So we are always stucking in between that why and how. So instead of understanding the what, so really we need to understand what about the quantum mechanics, then definitely we can go ahead for the why and how. So again, you can see here some problems like as I have just already discussed with you, if I cause spectra of atoms to contain discrete lines. So discreteness, you can see we are not getting the regularity in a spectra of items. So atoms basically, why it is? So it was apparent that only a small set of optical frequencies or the wavelength could be emitted or absorbed by the atoms. So as we know, if we see, if we go for the photoluminescence, then simply we know okay, which light can be absorbed by the material and which light can be emitted. So simply there are so many things which we can understand, and again we can see the base of number of theories are in quantum mechanics. If we want to see here, you can see each atom has a distinct fingerprint. So how do we know that atom has a distinct fingerprint? So we know if we are taking the X-ray diffraction pattern or the powder X-ray diffraction pattern of any of the material, then we know it must have a typical peak or the typical wavelength at which only it gives the peak. So that is why we can say that each atom has a distinct fingerprint. So that cannot gives us the peak at a very different value. So that is why we can see the every atom has means that can be explained or that can be elaborated just like a fingerprint. And as we know, the fingerprint of any of the human being cannot be same. So likewise, if we take the XRD pattern for two different elements, that cannot be same. So then light only comes off at very specific wavelength, as we know, the or frequencies or the energies. So as we know, like light is having a waveguide like a violet to red color, and then every color must be coming with a particular or the typical frequencies. And if there is a typical frequency, which means that there is a typical energy, and that we know E is equal to h nu, where h is the Planck's constant and nu is the frequency. So in that way, we can calculate the energy associated with any of the radiations quantum mechanically. So again, we know like a hydrogen atom, it's a very fundamental problem. So like with only one electron and one proton emits the several wavelength. It's a really fantastic theory or like a fantastic problem from which we can understand quantum mechanics beautifully. Because why people are just trying to understand the spectra of hydrogen atom initially? Because it's the simplest one. If we go for helium, if we go for like a lithium, boron, carbon, or anything, then again the difficulties or the intricacies will be increased. So just to avoid that, everybody trying to understand first theory of hydrogen atom, and then they can extend to other atoms or the other molecules. And that is why we know, so we can see initially that the like a scientist have applied the quantum mechanics or the quantum phenomena to the hydrogen atom only. Then again we can see then now you can, if you see or if you study the stories behind quantum mechanics, then we can observe number of things are weird, number of things cannot be understood by the common man. How it is, why it is, how it is happening, why it is happening, how like light can be used like a particle as well as the wave. And again, if we go back, then we know the Newton has given the Newton's corpuscular theory, where he said there is ether medium and then the light can travel only through the ether. But again that was failed, and again the wave mechanics came into the picture. Like a wave theory of light came into the picture, not wave mechanics, the wave theory of light came into, and then they proved there is means there is no requirement of the medium to travel the light. And that was proved कि light can scatter, light can like a transmit, right, light can reflect, light can diffract, light can polarize. So these all phenomena supports the wave nature of the light. So that we can see. So without quantum mechanics we could never have designed and built. So now you can see, if there is no quantum mechanics, then we don't have the devices like mobile phone, we don't have the devices like a laptop, computer, televisions. It's really difficult to have this type of the devices, and that is why quantum mechanics plays a very important role. Again, as we know, if we want to understand the semiconductor devices like a computer, cell phones, so how it comes, when it comes. So whenever just I am trying to teach the semiconductor, so then we know semiconductor can, or any of the material like or material can be distinguished like a conductor, semiconductor and insulator. Then we should understand how and on what basis we can distinguish these type of the materials. So then we know there are two bands, we called it as a conduction band and we called it as a valence band, and in between that the gap we called as energy gap. So now that energy gap distinguishes the material from conductor, semiconductor and the insulator. Now the question arises, from where this band came into the picture. Band is what? It's nothing but the stacking of energy levels. Now from these energy levels came from where? So that the genesis of this energy level or the splitting of energy levels is related to, as you may be knowing, the one dimensional potential well problem that gives us the solution of the Schrodinger equation, and that comes out to be En is equal to n square hs square upon 8 ml square. And that En from n is equal to, as you may be knowing, from 1 2 3 4 onwards, gives us the energy level. And that when this energy level comes closer or stacking together, then there is a formation of the band. And how you can see how the quantum mechanics supports to semiconductor physics. Otherwise it is very much difficult to understand the phenomenon. And as we know, that particular modulating the energy gap gives us the fantastic application, and that leads to optical application, that leads to that leads to the ceramic, and that leads to dielectric material, even though magnetic material. So everything is related with the band gap. And now you can see the band from where it comes. So if we see in detail, then we must understand and we must thankful to the quantum mechanics for giving the fundamentals, or the for giving the this kind of the explanation in a very early days. So that helps scientists or the researchers to develop the devices. So then again, another device is, as we know, the lasers. So if we want like a laser, as we know how laser can be generated. So as we know, the laser can be generated in which region of the spectrum. So friends, for that you may be knowing the ruby laser, helium neon laser, some CO2 gas laser, and then we know the emissions also. So then how that laser can be generated, or how that laser can be built. So again, there is a involvement of the quantum mechanics, and if we see in deeper sense, then we can understand, yes, laser is again one of the genesis of the quantum mechanics. As you may be knowing, the phenomenon of the stimulated emission was given by Einstein in 1929, but the first laser came into the picture in 1960. But that the genesis of that stimulated emission was there in a quantum mechanics. If it was not given by the like Einstein, then definitely it may be prolonged, or it may be difficult to understand the phenomenon of the laser. So in that way, we need to connect different physics to understand the quantum mechanics, and again we can apply quantum mechanics for solving different problems also. So again, another medical devices, as we know, like MRI, magnetic resonance imaging. So with the help of that, as we know how the body can be scanned, and like a doctor knows how or where some like anomaly or something is there. So friends, again, the genesis of this MRI, or again you may be knowing superconductivity. If you want to explain the superconductivity, again you need a quantum mechanics. And then again, MRI is one of the example or the application of superconductivity. So in that way, so we can see how quantum mechanics is important. Then like a nuclear reactors, atomic clocks, now we know the GPS, navigation. So these all are existing only because of the quantum mechanics. So you can see the physicist didn't embrace quantum mechanics because it was like a novel, then like or the weird. So we have to accept it. Sometimes we feel, even though when I was student, I used to feel, Arey, how difficult this mechanics is, quantum mechanics is. But when we just trying to understand the phenomena, trying to correlate with some different applications, then really we thought yes, it's amazing physics. And that is why, my dear friends, I'm just suggesting you to read this particular physics carefully. Read and try to understand how this particular physics will help for solving the different problems. So like let's start. As I told you, if there is no Planck's or the Planck's constant, then it would be really difficult to explain and understand the quantum mechanics. As we know, we are saying that E is directly proportional to nu. Nu is the frequency of light, E is the energy. But if we want to remove the proportionality constant, then it comes like E is equal to h nu, where h is Planck's constant. So that gives us the birth of quantum mechanics, and that is why this h is equal to 6.63 into 10 to the power minus 34 joule second is the very much important value in quantum mechanics. And that gives us the theory of how much energy can be liberated from any of the atom having a frequency, or the having the like a frequency, or like bombarding with particular like energy or what. So as you may be knowing, the genesis of atom bomb, or like number of nuclear reactions. So that also occurs because of this particular equation. So as we know, so if we are talking about photons, then photons are associated with the, as we know, so these photons are associated with, or the photon has, like you can see, frequency, wavelength, speed, or it travels with the speed of light. Energy is always E is equal to h nu. Then momentum always equal to like a P is equal to h nu by c, and that can be considered as a h is equal to Planck's constant. So this is what like important things that gives birth to the quantum mechanics. Then you can see here unification in physics. So like people were just trying, or the people, instead of people, I can use the word scientist. They were trying to do some unification, like unification in between the mechanical theory. You can see that was given by Newton around 1687. And again in mechanical theory given by the Newton, so what entities he has considered, like a particles, inertia, force. So that lies along a line between interacting particles. But whereas in case of electromagnetic theories, like electric and magnetic field, they have considered force that is perpendicular to both field and motion, that also considered. So in that way, you can see how different phenomena or different aspects were considered in case of mechanical theory and electromagnetic theory. So again, different kind of the motions you can see given by the mechanical theory, like a celestial motions, terrestrial motions, motions in three dimensions, or the heat. But again, in case of the, with the help of electromagnetic theory, it has been explained like magnetism, electricity, and optics also. Then again, around 1905 and 1916, some of the phenomenon was explained by Einstein with the help of relativity. So, but again, as we know, with the help of these all theories, or these all theories were not sufficient to explain the different or the all phenomenon, and that is why some unification should be there that can help us to explain the phenomenon, means phenomena that was earlier explained by the mechanical theory or the electromagnetic theory, or we call it Newtonian mechanics, or like by using electromagnetic theory. And that is why if we see the chronology, then in 1900 Planck came into the picture. Then Einstein in 1905 gives some theory, like in 1916, then 1917. Then again, the Bohr and Heisenberg, as I told you, like Heisenberg's uncertainty principle, so that supports the Bohr's theory of non-existence of electron inside the nucleus. That was like confirmed in 1925. Then Schrodinger, as we know, the Schrodinger equation is most important equation in terms of quantum mechanics, like a time dependent and a time independent equation. Then again, as we know, as I have said, the quantum mechanics can be distinguished into two types or can be explained with the help of wave mechanics as well as the like a matrix mechanics. And that is why again here we can see the Dirac who has given different notations how quantum mechanics can be explained with the help of that. Then like a different functions also comes into the picture, like 1927 you can see Dirac, then the Bethes, Tomonga, then the like a Schwinger, Feynman and Dyson, 1940s, and then they just tried to elaborate, tried to explain different phenomenon uh, occurred in nature as well as occurred artificially with the help of quantum mechanics. And then they found some good results, and because of these all results, they said, okay, this physics is acceptable. Else earlier everybody had a thought this cannot be happened, this cannot be happened. But when it was applied for making some devices or for like solving some problems, then everybody has accepted, okay, quantum mechanics is the like a real physics. Earlier everybody said it's a probabilistic, it's just assumption based physics, and that is why it's very much difficult to accept and solve some problems with the help of this particular physics. And that is why you can see it dissolves the classical distinction between points, particles and non-local fields like waves, and quantum objects manage both at once. So that happens. And you can see, and then there were we can say that the end of the mechanical age. So but still we cannot say there is an end of this mechanical age, but still, so just to understand in a better manner, we can say that around 1900 there was an end of mechanical age, and then like quantum age, quantum era came into the picture. So like here we can see things move in a continuous manner. All motion, both in the large and small, exhibits continuity. So that was again proved with the help of the quantum mechanics. So why and at what condition things can be can gives us the continuum or the continuous spectra. Then like things move for reasons. All motion has a history, is determinable and predictable. So even though earlier to that, so it was really difficult to predict the motion of an electron or motion of a small particle, but with the emergence of quantum mechanics it is possible. And as we know now like we can see we are having like some screen coated with some phosphor material, and then with the help of that we can see how the trajectory of an electron, and that we can see with the help of CRO, you may be knowing, in our laboratory, cathode ray oscilloscope. So where we can apply different magnetic field, we can apply different electric field, and if we combine the effect of magnetic field or the electric field, or if we change any of the parameter, then also we can see how the trajectory or the how the motion of an electron is there. So that is also there. Then the universe and all its constituents can be understood as a complex machinery, each component moving simply. So that also proved by quantum mechanics. Then again you can see a careful observer can observe physical phenomena without disturbing them. So earlier what happened, everybody, when anybody want to see like any of the cells, or if we go for biological objects, then they have to disturb it. Or if people wanted to study the materials, so then they have to disturb it to understand the basics behind that or the story inside the material. But with the emergence of quantum mechanics, as we know, so like if we want to see the image or the surface of any of the material, then with the help of scanning electron microscopy or the scanning tunneling electron microscopy, so we can see the image, we can see what inside the material, how fracture is there. So where fracture is there in any of the material, that can be seen. But earlier it was very much difficult to understand the fracture like phenomenon, or like any of the phenomena that can happen inside the material. So now it's easy. So inside the atoms all of these statements proved false. So now again you can see what went wrong. So it's really like amazing to understand the quantum mechanics. And if we understand the quantum mechanics, or like how how there was a shift from classical to quantum mechanics, then and then only we'll be able to solve the objectives. Otherwise, really difficult to have the insight about solving the numericals or solving the MCQ pattern questions. So, like you can see, the classical physics could not explain the line spectra. That was the first thing. Always you remember, you may get some questions based on this also. So, classical physics could not explain the line spectra. From where? So, as you may be knowing, the line spectra from the atoms basically. Then, like electron configuration in atoms. Then, black body radiation. That was the very big disaster in terms of the classical mechanics. Then another thing is the like a then again, that gives the birth, basically, we can say birth to the quantum mechanics. After that, another phenomenon was like a photoelectric effect, then photoelectric effect followed by the Compton effect, like Compton scattering of the X-rays, is again one of the beautiful experiment from where we can understand how we can see the like a Compton shift, and Compton shift is nothing but the difference of two wavelengths, and that gives us like a support to the particle nature, and that particle nature, like a photoelectric effect, Compton effect, gives support to the particle nature of the light, and that is really essential. Then again, a specific thermal capacity of the crystalline solid. So these all leads to the quantum theory. And again, as we know, the quantum mechanics is not only physics; it is the quantum chemistry also, because means that we cannot say that it's a physics; it's a quantum mechanics, and that can explain the physical as well as the chemical phenomena, and not only the simple phenomena, but that can be extended to superconductors, that can be extended to, as I told you, laser physics also can be explained with the help of this type of the phenomena. So let me conclude in a 2 minute. So like simply quantum field theory that we'll see in next class also. So let us conclude what we have done in today's session. So we have just started with like a how there is a genesis of the quantum mechanics, and what are the different challenges in quantum mechanics or understanding quantum mechanics. So like the first part of your syllabus, like quantum mechanics, wave particle duality, that also we have seen. Then the Schrodinger equation, time independent, time dependent, that we will see in upcoming classes. So friends, now just at the end I am saying कि don't take quantum mechanics as a tough physics. Try to understand basics, then and then only you will be able to explain more. So here I want to stop for today's session. So thank you once again, thank you everyone for joining with us. Thank you so much. Have a nice time. Happy, just enjoy learning quantum mechanics. Thank you.